This ECE 201 lesson is titled Equivalent Sources and Source Transformations. In a previous lesson, we saw how resistors could be combined in parallel and in series into one equivalent resistance, how this did not change any of the voltages and currents in the rest of the circuit, and represented a circuit simplification. Simplification is good. Let's see how we can apply that in this lesson to sources of electrical energy, voltage sources and current sources. So on the board here we have a rest of the circuit connected to 3 voltage sources in series. Our claim will be that we can replace those 3 separate voltage sources by one equivalent source whose value is equal to Vs1 plus Vs2 plus Vs3. This may seem intuitive enough, but how would we show that to a skeptic by using element constraints and connection constraints? Well, look at the voltage and current associated with the rest of the circuit. By Kirchhoff's voltage law, V is equal to Vs1 plus Vs2 plus Vs3, and that regardless of the value of the current. That's the same that we would have if we replace those 3 voltage sources by one source with the value Vs1 plus Vs2 plus Vs3. So let's draw a new circuit on the board. Here we have an equivalent voltage source whose value is equal to the sum of all the in-series voltage sources. That change will leave the currents in the rest of the circuit and voltages as well unchanged. It's an equivalent source. One needn't look far to find cases where circuit designers have used the fact that 2 voltage sources in series are equivalent to a source whose voltage is equal to their sum. In this camera here, if we open the battery compartment, they are connected in series within the camera to provide the equivalent of one 3-volt source. On the other hand, taking a different camera, if we open its battery compartment, we find just one battery. It's approximately 3 volts lithium-ion single battery. The difference between the two being a matter primarily of milliamp hours, consumer preference, and cost. Current sources, however, can be added in parallel. Here we've got 2 current sources in parallel. From the rest of the circuit's point of view, if we look at the voltage and the current, by Kirchhoff's current law, this current I is equal to IS1 plus IS2 regardless of the value of this voltage, so we can simply replace those 2 current sources by one equivalent source, and the value associated with the equivalent source would just be equal to the sum of the individual current sources in parallel. So we can replace current sources in parallel by an equivalent equal to the sum, voltage sources in series by the equal to a sum. Those 2 facts might seem rather intuitive. Let's now consider a perhaps less intuitive case. Let's say that I have a resistor and a current source. It's connected to the rest of the circuit, but there's some resistor in series with it. Now, from the rest of the circuit's voltage and current, that resistor plays no role. If I look at the voltage at the rest of the circuit, the current associated with it, that current is equal to Is, independent of that resistor. So the equivalent of this part from the rest of the circuit's point of view can just be the current source. We can eliminate that resistor. Or in a variation on this, let's suppose that we have a voltage source in parallel with the resistor, Vs. From the rest of the circuit's point of view, the voltage V is going to be equal to Vs. The presence of that resistor does not affect any of the voltages and currents in the rest of the circuit. So we could say, as far as the rest of the circuit is concerned, we can just erase that resistor and all the I and V in the rest of the circuit are the same. In this cartoon of Celine with her circuit in room A, which is connected to Joan's circuit in room B, none of the V and I that Celine's measuring in room A would change at all if Joan removed the parallel resistor. And now Joan's removed that resistor. It's equivalent from Celine's point of view. She represents the, quote, rest of the circuit, end quote, point of view. Of course, from Joan's perspective, it's not the same circuit. Before she had a resistor that was dissipating power. Now she doesn't have that resistor. But from the rest of the circuit's point of view, it's certainly an appropriate simplification. And now let's consider something more subtle, the idea of source transformations. If connected to the rest of this circuit is a voltage source in series with a resistor, we may show, and we will show here, that from the rest of the circuit's perspective, we can replace this voltage source in series with a resistor by a current source in parallel with the resistor. So how does that come about? Consider that we're dealing with linear circuits, so the relationship between current and voltage is linear. Then if we make a plot of I versus V, current versus voltage, the result will be a straight line. It's a linear circuit. And any 2 points make a line. So if we have 2 different circuits and find that they share the same 2 points, then they have the same line and the same relationship between current and voltage. In particular, let's focus on 2 of these points. This current, the vertical intercept, is where the voltage is 0. 0 voltage is a short circuit. We can say that's the short circuit current. This intercept on the horizontal axis is when the current is 0, open circuit. That would be the open circuit voltage. If we can show that 2 circuits have the same open circuit voltage and the same short circuit, then they have the same IV characteristics and they are equivalent. This equivalency, of course, assumes that we're dealing with linear circuits where there's a linear relationship between I and V and 2 points are sufficient to make a line. Here, for example, we have 2 circuits, one right on top of the other. The first consists of a 10-volt voltage source in series with a 10-ohm resistor. And I wish to know what's the open circuit voltage here. There's no current flowing through this resistor, so there's no voltage drop across it. So by KVL, V open circuit is equal to 10 volts. So this is equal to 10 volts. Let's turn our attention to the bottom circuit, which consists of a current source in parallel with the resistor. All of this 1 amp is going to flow down through this 10 ohm resistor by Kirchhoff's current law because there's no current flowing through the open circuit. And by Ohm's law, the voltage, the open circuit voltage, is 10 ohms times 1 amp. That's equal to 10 volts also. So we can say, these circuits have the same open circuit voltage. That's 1 point. We only need 1 other point to make a line. Let's look to see what the short circuit current would be. Now we've redrawn the circuit showing that a short circuit is connected to both of them. We want to know what's the I short circuit for the top and bottom circuit. There's 0 volts, of course, across the short circuit. So that means that by KVL, there's 10 volts across this resistor. We have to have 0 minus 10 plus 10 is equal to 0. So the current flowing through here, which is the short circuit current, is 10 volts divided by 10 ohms, or 1 amp here. Now how does that compare with the bottom circuit? For the bottom circuit, we have 0 volts because of the short circuit, 0 volts across the short circuit. There has to be 0 volts across the 10 ohm resistor. Therefore, by Ohm's law, there's no current flowing through that. So by Kirchhoff's current law, this 1 amp will all go through the short circuit. So this is also equal to 1 amp. Thus, these 2 circuits do indeed have the same short circuit current, the same open circuit voltage. They are equivalent from the rest of the circuit's perspective. And this is an example of a source transformation. we transformed a voltage source resistor combination to a current source resistor combination. And as it turns out, as we proceed with methods of circuit analysis, mesh current analysis, node voltage analysis, such transformations will be useful for us in reaching a solution. In this picture, Joan's circuit in room B consists of a 10-volt source in series with a 2-ohm resistor. Celine's circuit in room A is connected to it. Then Joan makes a source transformation, replaces her part by a 5-amp current source in parallel with a 2-ohm resistor. After Joan's source transformation in room B, nothing's changed in room A. Let's apply equivalent circuit concepts to this circuit. Suppose that my focus is, what is the current through this 6-ohm resistor? You can see the connection points here. So let's try some of these equivalent circuit concepts. Here's a 40-volt source in series with an 8-ohm resistor. Suppose we do a source transformation, the current source. And we have, this is what the circuit looks like after the transformation. Now I see two 8-ohm resistors in parallel. So those can be combined from the rest of the circuit's point of view into one resistor. 8 ohms in parallel with 8 ohms is, of course, 4 ohms. It's a 4-ohm resistor. And now I can do another source transformation. 5-amp source in parallel with 4 ohms is the same as a 20-volt source in series with the 4-ohm resistor. Shall we do that? We now have a voltage source again. Value is equal to 5 amps times 4 ohms, that's 20 volts. There's the 4-ohm resistor. And now when I look at this current that I want to get, I could say that this 20-volt source is seeing 4 ohms in series with 6 ohms, so that current is 20 volts divided by 10 ohms, or in other words, the current is equal to 20 volts over 10 ohms, or 2 amps. Now compare what we've done here to starting with KVL, KCL, element constraint, and writing down X equations for X unknowns. Have we somehow gotten around KVL and KCL and Ohm's law and so forth? We have not. All of these methods, putting resistors in parallel and series, source transformations, are all based on KCL, KVL, and the element constraints. What we have come up with is more efficient ways of solving for a variable of particular interest. And with that example, that concludes our lesson on equivalent sources and source transformations. We will be making much use of equivalent circuit concepts throughout our treatment of circuits.